Hello again. This is Math 1428, remote delivery for April 20th, 2020, and this is going to be section 6.1 content from your book, and please use keys like this. I'd like to open just by reminding you that I'm very proud of you, and I'm thinking that there are going to be champions among you. These champions are going to be the ones who have the will to stay the course, to earn the grade, and not to have their goals deferred. Be the champion. In section 6.1, we're studying system of equations in two variables. Usually these will be x and y. So we're going to learn how to solve them by graphing. We're going to learn two algebraic techniques for solving them, one called the substitution method, another called the elimination method. And as always, there are word problems because life is a word problem. A system of equations is two or more equations that have to be solved simultaneously. Here's an example of a system of two linear equations in two variables. The only thing that is a solution is something that makes both equations true. So for example, we will find that 2 comma minus 3 is a solution to these equations because when we substitute into the first equation and into the second equation, they both are true. Let's look at another example. Here are two equations, two linear equations for us to solve. So we graph both of them. We graph the second one, that is this green color, and we graph the first one, which is this red color, and we see that they intersect at 2 minus 3, just as we spoke about before. We can use our calculators, but if we're using our calculators, so we have to put these in slope-intercept form because that's what happens in the y graphing screen. But you can do that, and then you can find the intersection between these two curves using the intersection techniques that we talked about previously in the course. In any event, the answer to this is 2 comma minus 3. Now, that's one thing that can happen. We can have one solution and exactly one point in common. Well, we can have a solution where the lines are parallel. That means they never overlap. There's no common points, and there would be no solution. And we also can have a case where both of the equations describe exactly the same set of points. The lines are identical, and there are infinitely many common points, infinitely many solutions. If there are solutions, we call it consistent. So this one is consistent, and this one is consistent. If there is no solution, we say that they are inconsistent. If the lines are not multiples of each other, we call them independent. If they are multiples of each other, we call it a dependent system. Now, solving a system of equations is not always accurate if you do it graphically, because it would be difficult to figure out what these numbers are from a hand-drawn graph. There are algebraic methods for solving these equations, and when used correctly, give the right answer. One method is called the substitution technique. Let's talk about how that works with an example. So here we have the same two equations that we've been studying before. But the substitution technique says we take one equation, the first one, and we solve it for x. So we know that x is equal to y plus 5. So now we're going to substitute this into the second equation. Everywhere where there's an x, we're going to put y plus 5, and we're going to simplify that, and we're going to find that y is equal to minus 3. But then we can take the minus 3, plug it in here, and realize that x had to be 2. That's the substitution technique. Another algebraic technique for solving systems of equations is called the elimination method. With this method, we eliminate a variable by adding the two equations. And sometimes we have to do a little bit of work to do that, or sometimes it happens in an easier way. Let's use the elimination method to solve this system of equations. So what we're going to do is just add the two equations. If we add them directly, the y's will drop out, and you'll have 3x is equal to 9, so x has to be 3. But then what you can do is substitute 3 into either equation and solve for y. So if we go into equation 1 and we substitute 3 for x, we found out that y has to be minus 4, and we could check by substituting into both equations if we wanted to. The other thing that we would do if we were doing it graphically is we would have to get this in slope-intercept form, so we'd have to solve for the y, graph them, and then we again find that the intersection is 3 comma minus 4. This is elimination, this is a graphical solution. Now sometimes it's more complicated. When we look at this, we see that there's not a simple way to just add or simply multiply top and bottom. So what we're going to do is we are going to obtain coefficients that are opposite, but first we're going to multiply the first equation by 5 all the way through both sides. And the second equation we're going to multiply by 4 all the way through. Now the goal of this was to get 20 and minus 20, so when we add these we get, these cancel out by design. This ends up being 23y is equal to 115, and you solve that, y is 5. Then I back substitute into either equation. We're going to substitute into equation 1, so we're going to put y to be 5 in equation 1 and solve for x, and we'll get x is minus 1. So sometimes there's a little more work, but it's worth it to solve this. We also have situations, and here is we're supposed to solve these by elimination method. Now notice in each of these, the x is over the x, the y is over the y, and the constants are over the constants. X is over the x, y is over the y, and constants over the constants. So what we could see is if we considered the ratios here, I would have the ratio would be 1 to minus 2, minus 3 to 6, and 1 to 5. Notice that this ratio, minus 1/2, and this ratio is minus 1/2. That means the two lines have the same slope. But this means that the lines do not have the same intercept. That means there will be no solution. Now if you didn't realize that as you were starting, that's okay, but if you started trying to solve this by substitution, you would find out that 0 equals 7. That means that there's no values that would work because 0 is never equal to 7, so the solution is the null set. There is no solution. The set of equations are inconsistent, and the graphs are parallel lines. Over here, notice, again, the x's are over the x's, the y's over the y's, and the constants over constants. But here the ratio is 2 to 4, or 1/2. Here it is 3 to 6, or 1/2. Here it is 6 to 12, or 1/2. So you see, whenever we do some multiplications and add, we will get 0 over 0, because those are the same equations. That means there are an infinite number of solutions. Now, perfect your understanding by trying these examples. Let's look at a different kind of example. And there are examples in your textbook that deal with distance equals rate times time and mixture problems, which you can also solve with 2 equations and 2 unknowns, but we're going to talk about supply and demand. So suppose that the supply and the price of a satellite radio are related by this equation, and so y is going to be the price in dollars, and x is going to be x thousand units. But we also know that supply and demand for the same model are also related by this set of equations. Again, this is the price and the same set of variables. The equilibrium point is where the supply equals the demand. This is the demand equation. This is the supply equation. And you see we try to find the equilibrium point where they intersect. If you solve these 2 equations, you'll find out they intersect at 2 and 150. That means that the equilibrium point is $2,150, and that means that the equilibrium quantity is 2,000 units, and the equilibrium price is $150 per unit. Here's an exercise that you can test your understanding with. That brings us to the end of part 1. There's going to be a part 2 for this exercise, but chapter 6.1 or section 6.1 is finished. I will see you in part 2.